start, sir. Good afternoon to everyone. I am glad to inform you that we research scholars from the Department of ECE, with a great support and supervision from our faculty, are willing to initiate research scholar talk series named My Scholar Voice. The object of this program is to protect the expertise of the researchers from their domain to motivate the undergraduate, postgraduate students, and fellow researchers. In addition, one can get familiar with the research going on in different areas in the ECE department. This will surely develop the interest towards the research apart from the academics. The program is extremely beneficial for the presentees as well as the participants, as it will help to build up a strong research network where they can continue the research collaborations. For today's session, Mr. Vasudeva, one of the research scholars from the Department of ECE, is going to share his research expertise, his enlightening talk on design of digital circuits using quantum dot cellular automata. Mr. Vasudeva is pursuing his PhD under the guidance of Dr. Pradyut Kumar Sankhe, Department of ECE, SRM University, AP. He received the BE degree in ECE from Andhra University in 2013. He received his MTech in the Department of ECE with a specialization in VLSI and embedded system from JNTU Kakinada in 2015. He is very keen to continue his research in digital VLSI design, quantum dot cellular automata, and digital image and video processing. Vasu, continue your talk.
Good afternoon all. Thanks for a nice introduction. The title of today research talk is Design of Digital Circuits Using Quantum Dot Cellular Automata. Sometimes it is called as a QCA. QCA is an emerging technology for nano architectures, and it is one of the alternative technology for CMOS technology. Now we will start with the CMOS fabrication flow, and we will see the limitations of CMOS technology, and we will look into the QCA and see how to design QCA circuits using QCA circuits, and finally we will implement some digital circuits in QCA designer tool, and finally we will conclude research talk. Let me start the presentation now. Today's talk is design of digital circuit using quantum dot cellular automata. Now we will see. First, we will see the CMOS fabrication flow. I think everyone know very well why chart design is the most very important in CMOS fabrication flow. It will give design methodology starting. It will start from specifications and it will give the finally a fabricated chip. Basically, the Y chart having three domains. One is behavioral domain, and another one is structural domain, and last one is physical domain. Behavioral domain targets characteristics of the ICs, and structural domain, it targets structural detail components in the IC, and physical domain, it will completely layout and fabrication of CMOS circuits will be targeted. Basically, behavioral domain and structural domain both will be coming into the front end, and physical domain, it will coming into the back end. In front end, we will implement any architecture or algorithms. We will see the behavior of the algorithm. We don't want to see any circuits inside the algorithm. That we will check whether it will be working or not. After that, we will send to a structural domain. In structural domain, we will implement gate structure or flip-flops we will use, and transistors we will use, and we will implement the structure of the algorithm. That structural domain, later we will send it to physical domain. In physical domain, we will completely implement a layout, and that will be connected to the fabrication. Finally, we will get the chip design. In behavioral domain, focus more on algorithms and system design. In structural domain, it is style focus on structure and logical design. In transistor level design, focus on NMOS, PMOS, CMOS structures, and the layout design targets completely back-end design. The entire structure gives the foundry of fabrication. Now we will see the different type of packages type. Initially, In 1970, the IC or chip fabrication will be started. That name is DIP, Dual Inline Packages. I think everyone know, I mean, BTech students very well know. In our electronic labs, we are always use these dual inline packages. That IC we will placed in breadboards, and we will give the connections, and we will check the output of the IC. And after that 1970, so many IC methods, fabricated packaging type of ICs are there. In their quad flat and pin grid array, ball grid array, and chip scale packages. Some are ICs are, I mean, packaging types are all are available. In later we just know the different integration methods in VLSI. In 1964, they are starting small scale integration, that is called SSI. In small scale integration, where we are able to fabricate 1 to 10 transistors or 1 to 12 logic gates in a single monolithic IC. After that, they are increasing the number of ICs in a single monolithic chip in 1968. That is called as medium scale integration. Later, it is going to large scale integration. After very large scale integration, finally, it is coming to ultra large scale integration in 1984, where we are able to fabricate billions of transistors in a single monolithic IC. Now we will see these are the technologies nodes used in post 50 years onwards. It was starts from 10 micrometer technology in 1971. 10 micrometer means that will be channel length of transistor. After that, it is reducing the size of channel length. When we will reduce the size of this channel length, the number of transistors are increases day by day, and that will be reaches nowadays it is reaches 5 nanometer. After 5 nanometer technology, which is reaches 3 nanometer, 2 nanometer, and 1 nanometer technology, much of the improvement in performance of modern integrator circuits over the years has been achieved by reducing the size and thus increasing the density of the component devices. Now we will see why we will choose QCA technology. What is the drawbacks or limitations in QCA technology, that we will discuss. Actually, Moore's law, and empirical rules of thumb, which says that the density of components in integrated circuit doubles every 18 months, has held for 40 years or so. Unfortunately, this process cannot continue indefinitely. Current devices, when we are reducing the size of the channel length, I mean technology, when we will increase the technology, or when we will increase the number of transistors in a single monolithic IC, the CMOS technology problematic for number of reasons. For example, we will see the limitations in CMOS technology. It is almost reaches the end of the boundary. When we are increasing the number of transistors, first, as device set more closely packed, the amount of heat generated gets so large that operating temperature of the devices rise, degrading the performance of the device due to noise and electromigration in the metal interconnects. And second one is parasitic capacitor from the interconnects interface. So we overcome these and we need to overcome these limitations. We will implement QCA, quantum dot cellular automata. That length is proposed this QCA technology in 1993. This is one type of QCA nanoscale solution. Now we will see what is quantum dot. Quantum dot means in order to implement a system that encodes information in the form of electron position, it becomes a vessel in which an electron can be trapped or counted. Is there or not? For example, we will take one vessel like in vessel. Okay, we will take one vessel. Inside, we will is there. We will trap. If it is there, that we will consider some logic value. If it is not there, we will consider there is some other state of logic value. A quantum dot does just potential surrounded by a ring of high potential. Such rings are able to of sufficiently low energies at temperatures. Now we will see cellular automata. Cellular automata are discrete dynamical system whose evolution is based on local interactions. In 1987, proposed the probability of device that operates like CA, cellular automata, in the sense that they interact via, they are which have a finite number of states and whose evolution occurs at a state intervals. In another way, we will see the cellular automata array of finite state machines. Combining these two, combining quantum cellular, generally QC. So quantum dot cellular automata circuits consist of cells which are arranged in a grid fashion. With the charges means electrons, point to tunnel between the dots. Interface interaction affects domain over time. When we are taking QCS in between quantum dots interaction, but when consider quantum cells, Coulombic interaction. Like what is actually this QCM means it is a square shape. Square. It is a square shape cell. In this square shape cell having four corners having four dots. That is called quantum dots. In quantum dots, we will choose this. Electron to each in this quantum cell having two capacitive junction and two. When we vertically, horizontally it is having vertically it is having tunneling. The electron moving from vertical, it is blocked in the horizontal direction. First blocks the electron from moving horizontal direction is called tunneling. And it moves over based on repulsion. So we will consider binary. This is digital circuit. Actually, quantum dot is a QC technology is a digital technology. In digital circuit, it is having logic 0 or 1. When the electron is in this horizontal, that's why it is always in horizontal direction. When this horizontal direction, it is having horizontal direction, that we will consider as a logic 1. When it is this horizontal direction, that we will consider as a binary 0. So quantum dot one is 9, one is 45 degree cell, that is called rotated cell. Normal CMOS not only CMOS technology, in VLSI technology, the data will be stored, transmitted depending upon the voltage level or current level. That information is stored that transmitted depends upon the level of voltage. But in QCA, we didn't use any voltage or current. We are always consider the position of electron. So that position of electron will be moved. That didn't use any voltage level. So that's the reason QCA technology having very low power dissipation. Now we will see QCA representation. QCA representation, basically it is having stable and unstable two kinds.
So your voice is breaking.
Voice is breaking. Okay. When we are considering logic, this is logic 0 and this is 1. When we will consider logic 0 and logic 1, this is having some repulsion between these two electrons. So when it is having the repulsion, that means it won't stay like this pattern. This then that always it is having repulsion function. So the electron moves from lower to upper. So that will be moves in vertical direction only. That won't move in horizontal direction because of the capacitance junction. It moves from lower to higher. This condition we will consider as a stable condition. For example, we will connect to cells in adjacent cells like this, that time if we will give logic 0 and logic same values, logic 0, here also it is having some repulsion. So based on that repulsion, Coulombic repulsion, this won't transmit the data. So this condition also considered as an unstable state. So when we are applying the electron, so that time the repulsion will be applied and that electron will move to higher level to lower level. So this is logic 0 is transmitting to logic 1. So this is the stable state, and at the same time, this will be work as a NOT gate. Yeah, tell me, Thirumal Rao. Okay. Now it is okay. Voice.
Yeah, you can continue. So,
Okay. So this is considered as a stable state. Then it will be one of the NOT gate operation. In NOT gate operation, there is one more example is there, that was offset NOT gate operation. That is offset cell. When we are connecting two cells like this, that means normally the QCS cell having 18 nanometer size. When we will give one cell and another cell, we will translate 9 nanometer. That will be working like this. This architecture also working as a NOT gate operation. So this is also one type of stable state. Now we will see 90 degrees wire. In QCS circuit, we will transmit the electrons by using wire connection. I mean, normally VLSA we will use wire, but here we will connect array. I mean, QCS cells we will be connected in array form. That time it will be passes the data 90 degrees and 45 degrees. These two we will use for crossover connection. When for example, see in diagram, crossover, they have two type of crossovers. One is coplanar and another one is multi-layer. In coplanar, we will use vertically we will use 45 degrees cell, and horizontally we will use 90 degrees cell. That time the data will interact or interfere in one data will be interfere into another data, that will be passes, and the output will be coming as we want. In multi-layer crossover, they means there is a number of multi-layers are there in that layer as shown in diagram. So when we will use multi-layer, it will increases the count of cells, and it will increase the area of the circuit diagram. So maximum we will focus on coplanar crossover section only. We don't focus on multi-layer. And one more important gate is majority gate. In majority gate, basically, it is having 5 quantum cells. 3 quantum cells are input cells and 1 quantum cell is output cell. And the middle quantum cell we will consider as a decision cell. That center quantum cell, it will take the decision. When we are giving 3 inputs, the output should be changes based on the decision cell. Any one of, I mean, it maximum majority cell means the majority of inputs depend, output will be depending upon the majority cells of inputs. That we will see in next slide. For example, special case, we will take majority 0, 0, 1. One input is 0. 0 means that rotation will be negative. I mean, polarization will be -1. That rotation we will consider as a logic 0. And this is logic 1. That rotation will be positive polarization, and this is logic 0. So this majority gate that will taking the strongs always win the strongs. So strong always win, and that here the strong one is 0. That will give into the output cell, and output should be 0. In special case, another value 0, 1, 1 we will take, and when we will take 0, 1, 1, that will be here majority is 1. So that 1 is majority, that decision cell will take the decision 1, and that will be sent to output. Now clocking QCS. Actually, now we are seeing just basic gates. I mean, majority gate and inverter is the basic gates in a QCA design. When we are designing some digital circuits, that output should be depending upon the clock zone. In QCA, the synchronization is achieved by cascading clock for transfer the data from one cell to the next cell in order to propagate the information through QCA without any random adjustment of QCA cell. Basically, in QCA, we have used 4 clocks: clock 0, clock 1, clock 2, clock 3. And each and every cell having 4 stages, that are switch, hold, release, and relax. Each and every cell, every state having 90 degrees phase shift. When the switching state means, switching state is a polarization state. It moves the data from lower level to higher level, and the hold state is holding the data. When we are taking the output, that always we will use hold state. In hold state only we will take the data as a output. In release state, that is also one of the polarized state. In this release state, the data will be moved from higher to lower, and relaxed state is that is unpolarized state, that is completely in relaxed state. Now we will see 2:1 multiplexer using QCA. Already we know 2:1 multiplexer needed 2 AND gates, 1 NOT gate, and 1 OR gate. 2 AND gates means here we will take 3 majority gates and 1 is NOT gate. And S we will connect it like this. Already we have discussed about this, how it will be work as a NOT gate. And after that, in majority gate, when we are giving the negative polarization, that means -1, that will be work as a AND gate. So these two will be majority gates. I mean, green color having a two majority gates. That 2 majority gates work as a AND gate, and third one, we are applying the polarization is logic 1. That means positive polarization. That positive polarization, it will be work as a OR gate. So output should be giving the 2:1 multiplexer output. So here see the simulation results in QCA circuit 2:1 multiplexer using QCA. S is the selective line. I1 and I0 are the inputs. When S is 0, the output should be 0, 1. That follows the I0 value. When the selective line S is logic 1, I mean it is 1, that time it follows the input I1. Next, another one of small example of adder using QCA. Here also we are using of adder 1 AND gate and 1 XOR gate. For XOR gate, we have used majority gate. I mean, normally majority gate having 5 cells, but 10 cells majority gate also there. That by using the 10 cell majority gate, it will be work as XOR gate, and that was generating the output. That simulation results are shown in that. Everything we will see in QCA designer tool. Now we will see software tool for QCA circuits. Actually, QCA offers a GUI, I mean a graphic user interfacing, which circuit can be built for designing digital circuits using QCA digital circuits. There is 3 softwares are available in internet. We will use these 3 softwares are freely we will download. And one is QCA Designer, and another one is QCA Designer E, and third one is QCA Pro. QCA Designer E and QCA Designer, these 2 softwares will be working on Windows, and QCA Pro we will use in Ubuntu, I mean Linux. So QCA Designer E tool, it was generating it. I mean, we will implement digital circuit and we will simulate that one. But QCA Designer tool will give the number of cell counts, and it will give the area of the circuit. Only cell count and area it will give. But in QCA Designer E tool, that generating the number of cells and area, at the same time it will give the total energy dissipation and average energy dissipation. In QCA Pro, that will give this number of cell count and total area. At the same time, it will give the power dissipation, total power, average power dissipation, and minimum and maximum power dissipations also it will give. This tool is developed in the University of British Columbia to design and simulate this kind of circuits. Actually, there are 3 types of search engine simulation engines types are there. bistable, coherent vector, and coherent vector with W by energy. Normally, these three tools having bistable and coherent vector, and QCA designer E tool extra it is having coherent vector, that is W by energy. This when we are running the circuit by using coherent vector engine setup, that time only it will generate the energy dissipation. In bistable and coherent vector means it is taking 2 lakhs of samples, and it will run and it will take execution time more and more. But in bistable, we will give the number of iterations. Based on that, it will give the execution. It is a very fast executed simulation engine, and it is having very less execution time. To estimate total energy dissipation and challenges in QCA circuits. When we are trying to implement any digital circuit using QCA, we will reduce the number of cell counts automatically. When we will reduce the number of cell counts, automatically the area will be reduced. At the same time, we will focus on latency. Latency means number of clock cycles. Already we discussed clock zones, clock 0, zone 0, 1, 2, 3. Na? That we will reduce number of clock zones, then automatically it reduces the latency. When we will reduce cell count, area, latency, that time automatically the quantum cost will be reduced. We will focus on quantum cost mostly, and we will reduce the power and energy, a minimum power dissipation and minimum energy dissipation, and we will reduce the number of crossovers also, and we will reduce interconnections. Conclusion: low power dissipation, ultra high device density and speed. When we are implementing QCA digital circuits, we will reduce the power dissipation and energy dissipation also, and we will focus on to increase the speed of the circuit. And QCA technology would be used in future for develop a high-speed processor and ASIC that would be used for both general purpose and task-specific computing requirements. Thank you.
Thank you, Vasu. Any doubts from the audience?
Actually, I will show how to implement these small digital circuits in QCA designer E tool. I will show you. When we are installing QCA designer E tool, then this window will be open. In this window, having a file, edit, view, tool, and simulation. In file, we will already we have implemented any QCA circuits that we will open by using open. If you want to implement new one, you will implement by using new, and edit, we will edit, and we will use simulation. Here we will see simulation engine setups. Here having coherent vector, energy, and bistable approximation. Basically, QCA technology having some constant parameters. That was QCA cell size is 18 nanometer and dot cell is 5 nanometer, and the distance between two quantum cells is 20 nanometer. Based on that, we will implement these things. Now we will see cell means we will take one cells. When we will select cell, that will be displayed the cells, and we will take array means continuously we will give the cells directly. When we will select and we will remove this one, first we will see majority gate. For example, rotate, this option when we will select any one of the cell and we will click on the rotate, then it will be rotates that means it will be give the 45 degrees cell. Before that, it will automatically give the 90 degrees cell. And alt style means crossover. When we need to crossover, that means multi-layer, that time we will use this crossover. When we will use crossover, it will increases the size of the circuit. So maximum we will choose coplanar crossover only. Don't use multi-layer. And copy, when we will select some cells. For example, we will select these cells and copy, then it will copied, and we will copy and we will paste here like this option. Translate, mirror, these some options are there. Zoom in, zoom out, extend layer, everything is there. Now we will see how to implement one majority gate and AND gate, logic gates. So I will show you small circuits, so one or two. We will select cell. For majority gate, it is having 5 cells. We will select one cell, double click on that cell and give input. Label is, for example, we will give a input, and we will choose another cell and we will give another input B, and we will select another cell that we will give another input C. Now we will select output. So for that purpose, select cell and select this output. In label, we will give out. Okay, we are designing. We give the inputs and we will see how it will be give the output. When before start simulation, we will choose the selection. And first we will see bistable approximation. In option, number of samples and convergence tolerance and radius of the effect. That effect means only bistable only having this radius of effect. We will give 65. That will take the radius of 65 nanometer. If we will give 45 also, it will be work. And clock high, low, everything will be constant values. Don't need to change. Only you have to change radius of the effect and the maximum iteration per samples. For example, we will give 1000, 1 lakh, whatever you want, you will give, and you will choose animation. Then that time you have to see how the spin of electron will change. Then simulation, start simulation. See how it will be changed one by one iteration. They will give the animation. We will see based on that input value how it will change the output. Decision cell, how it will check. And bistable simulation, it is when it reaches the 100%, that time the simulation results will come. That waveform based, we will see the waveform, simulation waveform. So if A will be fixed and BC we will change, then based on that the decision will change. We are giving 1000 iterations now, that so it is taking more time. And bottom, see, this is the output waveform. So A is 0. So 0 means it is working as a AND gate. One iteration we will fix, then remaining inputs will be output. Remaining two inputs, that majority gate will be work as a AND gate. So 0 0 0 0 1 0 1 0 0 and 1 1 output should be 1. So this work as a AND gate. When the one of the input is the logic 1, that time the output should be work as a, that majority gate should be work as a OR gate. 0 0 output is 0, and when the any one of the input is 1, output should be 1. So this is the operation. When we are choose simulation setup, simulation engine setup is coherent vector, and we will start simulation. Then it gives the number of inputs and number of outputs. This is the coherent vector simulation output. Here we will see the total cells are 5, 3 inputs and 1 output. And the execution time is the total simulation time 48 seconds. It is taking 5 lakh samples. And the energy dissipation, total energy dissipation value, it is electron volt. Electron volt means already you know electron volt is 1.609 into 10 to the power minus 9. So based on that, we will taking the voltage value. So average energy dissipation. Now we will implement okay, if you have any doubts regarding this software, let me know, I will explain. Based on this, we will implement any circuit and we will see how it will be work. Hello.
Any questions from the audience regarding the software or regarding the?
Thirumala Rao Kadiam raised his hand. Thirumala Rao, do you have any question?
Sir, now he can talk, sir.
Hello.
Yeah.
Hello, sir.
Thirumala Rao, what is you ask your question?
Sir, sorry, sir. Hello.
Yeah, you are audible.
Am I audible, sir?
Yeah, you are
Yes, yes.
No, sir. Nothing, sir.
We will take all the questions offline. Renuka, are you there?
Yes, sir.
Let us conclude.
Thank you, audience, for participating and spending your time. Thank you, Vasu, for your excellent talk on digital circuits using quantum dot cellular automata. Hope the participants gain an insights into digital circuits designing using the QCA. Thank you.
Thank you.
Sir, can I end the meeting, sir?
Yes,
sir.
yes.